Okay, guys, so in this video, let's see how to take care of imbalanced data in the knife-based classification algorithm. So if I'm trying to find probability that, let's say I have some features and they belong to class 1. These are my features, W1, W2 to Wn. This will be equal to probability of y equals 1 into pi I equals 1 to n, probability of W1, W2, sorry, wait. This will be Wi, right? It's the same thing. Given y equals 1, probability. And if I have probability of y equals 0 to w1, w2, wn, I have probability of y equal to 0 into pi I equals 1 to n p of wi by y equal to 1, right? Sorry, y equal to 0. Sorry. Now, look, if our data set is imbalanced and highly imbalanced, let's say the percentage of imbalance is such that y equals 1 is equal to such that the classes that make up y equal 1 are 90% of the entire data set, and the classes that make up y equals 0 are 10% of our entire data set. So even if all of this um, so even if this is similar, because here you're just taking the proportion, right? The words that appear in class 0 and the words that appear in class 1. This is just the proportion. Even if this is similar, this will highly tilt the probability in favor of class 1. This value here, because there's so much of class 1 when related to class 0, this will tilt the probability in favor of class 1, right? Because of this being unbalanced, because of this being very high, the data point, considering that these are equal in proportion, the data points will get classified as class 1, right? So if you take a performance metric such as normal accuracy, you would still get 90 out of 100. Even if you get all of this wrong, accuracy is still 90 out of 100, which on paper looks good, but in theory, in practicality, it's bad, right? Because we lost almost all of our classes that belong to 0. So how do you overcome this? So there are some ways to overcome this. The first one is, upsampling and downsampling, right? Upsampling, downsampling. What you do here is you essentially upsample uh, the class where y equals 0, and you downsample the class where y equals 1. So you basically add more data points over here, or you remove some data points over here. Now, in theory, we don't want to remove data points. Sorry, in practicality, we don't want to remove data points because in real life, data is very hard to collect. So downsampling, where you try to remove data points to the bring the classes where y equals 1 to equal to 0, is not really done. We usually go with upsampling. The reason is simple, because in reality data is very hard to collect, and you don't just want to throw away that data. So instead you upsample. What you do in upsample is that if I have 10% in classes that belong to 0 and 90% in classes that belong to 1, I'll just add the same points over and over again 9 times, such that this proportion is equal to this proportion. That's it. I'm just the same data points that have class equal to 0, I'm just adding them again in the data set 9 times, so that this proportion is equivalent to this proportion. Okay. And one other hack is that you can just simply remove uh, both of py equals 1 and py equals 0 over here in the formula. If you look at this formula over here, you're multiplying it, right? You can just remove it. If you remove it, you're basically saying that both these classes have a probability equal to 1, right? You can remove that. But again, if in that case then this can lead to some troubles, because you're still multiplying the conditional probability of the word of the feature given the class equals 0. This can lead to some problems. So even though on paper, this is another trick that you can use. You can just remove probability y equals 0 or y equals 1 from this formula. You can just do away with it. In practice, we don't do that. We usually stick to upsampling of the class that has a lower representation in the data set, which in this case is y equal to 0. Now, one other thing which people can assume that happens is, when you set the value of alpha, like we saw in the previous video on additive smoothing. If you set the value of alpha to something, let's say alpha is 10. Now let's just take for example that my class 0 is very my class 0 is very small, right? So let's say I have 100 data points that belong to class 0, and two of them, there are two words. Let's take some feature wi's, just one feature, just for the sake of understanding. We take the feature wi. The feature wi where class y equals 0, there are 100 points where class y equals 0, and the feature wi appears 2 times in those classes. Whereas if we take the class y equals 1, let's say 900, okay? There are 900 data points where the class y equals 1. And the feature wi appears 18 out of those 900 data points. So if you observe carefully, this is both 2% of the entire data set, okay? This is 2% of the entire data set. So if you look at this, if I add my alpha over here, assuming k is equal to 2, I get 2 plus 10 upon 100 plus 10 into 2, okay? And I get 18 plus 10 upon 900 plus 10 into 2. Okay, so this is equal to 12 by 120, and this is equal to 180 by 920, right? So this is almost equal to 10%. So you see how alpha has affected your proportion over here for a particular feature. It's increased the representativeness of the feature in your data set for that particular class from 2% to straight up to 10%. Over here, it's not as much. I think this is about 5%, close to 5%, right? So your alpha can also play a very important role in trying to decide or in trying to subdue the adverse effects of imbalanced data class. If I increase alpha a little more, this can increase a lot higher, whereas this will increase only less. So I can choose a value of alpha in a particular way such that both of these are almost close to one another. But again, that is very tricky because as we all saw in the previous video, that changing the value of alpha also changes the representativeness of a word or a feature in the data set. Alpha in a way decides how important that feature is in the data set. So we don't want to meddle with alpha a lot. It's used for hyperparameter tuning and to see which value of alpha gives us the best value in our test data set for some performance metric. So in practice, we usually stick to upsampling and downsampling, but I just want to drive home the point that alpha can also be used. If you're a smart engineer and you're designing a system, you can also use alpha for taking care of your data set and making sure that it's not imbalanced.